Okay, hopefully in the last video, you've already been through the notes that walked you through an exploration in regards to linear, exponential, and quadratic. If not, I would recommend going back and doing that first. Those filled in notes and exploration will count as an assignment on your grade. This video is just going to walk you through some specific examples. So you will be asked to identify whether data given represents a linear, exponential, or quadratic pattern, and then actually create those specific functions based on what kind of data is given and pattern that is identified. So I'm going to go through some specific examples with just points, data given on tables. You'll notice a lot of times we write our tables vertically with our X and Y here. Your tables in your textbook are written down horizontally, so I did that as well. So I'm going to walk through some of these examples, and you'll be asked to do this on your assignment, so hopefully this will give you some specific direction if you're stuck. So linear, exponential, quadratic, just really quick reminding ourselves, one of the easiest ways to check the data is if you can plot data onto a picture or a graph. Then we can identify what kind of pattern it has, because linear functions always make a straight line. And exponential functions, remember, they increase from a certain value, or they decrease. So they may go like this. And there's some sort of horizontal asymptote that they get closer and closer to, but they never, ever touch. Quadratics, on the other hand, are symmetric, and they always make that U shape. We've dealt a lot with quadratics this year. They may be reflected or upside down, right? Maybe they increase in value first and then decrease, but they're always symmetric, and they always make that shape that we called a parabola. So let's look at some of the data given and see if we can tell what kind of function it would represent. So on this first one, I'm going to look to the left here. There's some data points given, and it asks me to, you're going to be asked to graph. So I'm going to plot these, which means this first one goes 8, 4. So I'm going to go to the right 8. I'm going to go up 4, then I'm just putting a point. The next point is 4, 0. So that would be over to the right 4. 0, negative 4. So this one doesn't move right or left at all. It just goes down 4. I've got negative 2, negative 6. So I'm going to go to the left 2 and down 6, and then negative 4, negative 8. So I'm going to the left 4 and down 8. Now if I play this connect the dots game, you'll notice this is the only data I was given in this whole pattern to assess from. So I'm going to assume that because those create a perfectly straight line, that this data represents a linear function. If we move to the middle one, and I'm again going to plot these points, I'm going to go 0, 2, which is up here, and 2 to the right, up 8 for the next point there, 2, 8, 1, 4. So this one's definitely not linear. Negative 1, 1, so I'm going to go to the left 1, up 1, and then I have negative 2, up 1/2, so I'm going to go halfway up there. You'll notice this one looks to be exponential, so it has that different rate of change there, and it's increasing. Now we're only going off of what data is given to us, so we're assuming that what we're looking at there is exponential. And then on the right, we have negative 1, 5. So I'm going to go to the left 1, I'm going to go up 5. The next point, 2, negative 1. I'm going to go to the right 2, down 1. 0, negative 1. Looks a little crazy. 3, 5. I'm going to go to the right 3, up 5. And then 1, negative 3. So this one right here definitely creates that parabola look. It's symmetric. So we know that this one must represent a quadratic function. Okay, so from points given, you're just going to plot those on the graphs that are provided to you, and you're going to identify what kind of function it represents. From a table, we can tell based off of the growth or pattern with the outputs. You're going to notice on all of the tables, I start my tables at different spots, like some start at negative 2, some at negative 3, this one down here at negative 1 as far as the x values go, but they're always consistent. So there's no weird funky relationship with my x values. If there is, then it's hard to tell what the pattern is going on with the y values. So as far as the x values go, I just make sure those are consistent and good, and these ones are all just fine. So we're going to immediately go to the y values, and we're going to look at what's happening with our output values. And again, all data sets have different relationships, and so if we can figure out if it's linear, exponential, or quadratic, we can find the pattern here. So if we look at 11 and 8, if I'm going to go from an output value of 11 to 8, looks like that would be subtracting 3 as its difference there. The difference between the value 8 and 5 is also 3, so it looks like we're subtracting 3. 5 to 2 is also subtracting 3. You'll notice that this pattern is consistent. And on the exploration, one of the things we realized when we were doing those plant growth is that when the first difference, right, is consistent, so we call that a common difference. If it's adding or subtracting the same number, then that is a linear growth pattern. That is constant. On this middle one, if I'm looking at the pattern between my output values, notice that to get from 1 to 2, it could either be that I'm adding 1 or that I'm timesing by 2. If I look at the next one from 2 to 4, that one adds 2 or timeses by 2. So you can kind of see that, like this one right here, the pattern is not addition, but rather multiplication. So here we're multiplying by 2 consistently every time, so that dot means multiplication. If the first difference is multiplying, we call that a common ratio. And I don't know why I wrote first, but if it's multiplying, then we're looking at an exponential function. So if that first ratio there between the values is consistent, then we know that it's an exponential function. Okay. The last one is going to be quadratic. I'm going to show you kind of what this looks like. So if we look between these values, we know it's not multiplying by anything. But if we look at the difference between them, to get from 11 to 5, I would need to subtract 6, right? There's 6 units different on the number line. To get from 5 to 3, we're subtracting 2. If I want to go from 3 to 5, now I'm going back up, so I would be adding 2. To get from 5 to 11, I'm adding 6, and 11 to 21 is adding 10. Notice there's no real pattern in the first difference as far as a consistent difference or sum. But if we look at what we call the second difference, so the difference between these values, -6 and -2, those are 4 units away on the number line. So to get from -6 to -2, I would add 4. Same thing with -2 to +2. I would add 4. 2 to 6, also adding 4, and 6 to 10, also adding 4. Oh, I wrote 10. If the second difference is consistent, then we know that this one actually represents a quadratic function. So that second difference denotes quadratic. Okay. I'm going to show you just really quick on the next ones how that works again. So again, if I'm looking at this one, I'm always looking at those first differences there. And if to get from -1 to -2, I'm decreasing by 1. To get from -2 to -1, I would increase by 1. -1 to 2 is going to add 3. 2 to 7, I'm adding 5. 7 to 14, I'm adding 7. So in this one, again, if we look at the second difference, -1 and +1 are 2 units apart on the number line. 1 to 3 is also adding 2, so we can see that we're consistently adding 2 in that second difference. So this one would also be quadratic. Here in the middle, I'm moving to the left, going from 648 to 108. Maybe that's a little bit hard for us to tell what that would be, or from 108 to 18. But if we look at like 18 to 3, if I want to get from 18 to 3, I'd be dividing by 6. So we like to write common ratios as multiplication. So instead of dividing by 6, I'm going to write multiply by 1/6. Same thing. And if you check in your calculator, if you take 3 and multiply it by 1/6, it does definitely give you 0.5. So if you can tell kind of what it's dividing by, just make that into a fraction. And we can tell that if it's multiplying or dividing by a specific value, it is exponential. Awesome. And then to the left, I'm going to do one more. So -4 to 1. That looks like I would need to add 5 to get from -4 to +1. Then from 1 to 6, I'm also adding 5, 6 to 11. 6 plus 5 is 11, and 11 plus 5 is 16. So this one appears to be linear. It has that consistent first difference. Okay, so you're going to practice this skill, and then in the next video, I'm going to talk about how we would actually create the equations to represent those functions.